All right, Graham told me, what did you say? Be careful what you say, or what is it? Just say good things. I don't know, what other things could I say? Basically, Graham needs no introduction, so maybe I'll skip it. But Graham is, a world-leading expert in atmospheric radiation, remote sensing, and he's the PI of the CloudSat mission. And you're a fellow of AMS, AGU, AAAS, and the UK Royal Society, a member of National Academy of Engineering, and you got several awards. Graham got several awards, including the Charney and the Aughton Award from the AMS. And for the last 8 years, he played a critical role in the international climate community by co-chairing GWEX, which is a key component of the World Climate Research Program. And he moved definitely to the US in 1984, right? Yep. To become associate professor at Colorado State, then professor, then university distinguished professor. And then in 2010, over Thai food and, what was it? Red wine, Graham saw the light. And he realized that the real action in climate science was at JPL. And he jumped ship, and 12 years later, here we are, and he's going to tell us everything we need to know about cloud physics from space. So thank you, Graham.
Thank you. Thanks. Well, welcome all. I realised I got a typo there. The sciences are not quite spelt right. I thought I caught them all, but... an early version of this talk I gave at the Royal Met Soc in the UK as part of the gold medal award that I got from the Royal Met Soc. My niece was spending some time working in England and went round to have dinner at her place the night before this lecture. And she asked me, what are you going to talk about? I said, well, I'm just going to talk about work I do. And so she and her partner, being young, they're able to jump straight in and find it online with their phone. And she looked at the title, Cloud Physics from Space, and she said, how can you talk about that for a whole hour? So I'm going to fill up the hour, and I'm going to tell you a little bit about a journey. This talk's more of a journey. It reflects back in the past and looks forward into the future. And this is a journey in time, mostly. And so I'm going to start with this outline. I'm going to start in kind of a curious place, weather modification, right? You might think that's most curious. And I'm going to kind of reflect on a pretty broad and significant shadow cast by four giants in our field of the second half of the 20th century. And then I'm going to talk a little bit about how cloud physics moved from a kind of a subdiscipline of meteorology to a kind of an important discipline itself of Earth sciences, Earth system science. And the climate change and the climate change problem brought this right to the fore as a kind of one of the leading areas of the science. And I want to introduce you to kind of some spaceborne perspectives, a few early results and a few results from the gold era. These are kind of just selectively chosen just to sort of make a few key points, and they're a little bit biased towards some of the work that I've been involved in, but nevertheless. I'm going to come back to the weather modification problem expressed or contrasted again with respect to this so-called aerosol indirect problem that represents the largest source of uncertainty as far as we know with respect to the quantitative estimates of the radiative forcing of climate and climate change. And then I'll leave with expectations for the future. So that's sort of the roadmap. It's kind of dense, and I'm going to skip through some bits and pieces kind of fast, but it's all there that we can go back to, and anything that's not clear we can go back to and ask questions. It's a primer. I'd like to just advertise. This is a rather wonderful book by Jim Fleming, a book on historical perspective, on the checkered history, as he says, of weather modification, basically, and climate control. So he touches on geoengineering in this book. So it's a great read. So anyone's interested in more broadly fixing the sky, weather modification, this would be a great read. Okay, so where we begin is sort of the post-war era. Started with the General Electric experiments by Schaefer and colleagues. I've only got any colleagues, and this is a picture of the experiments done in 1946 in the General Electric laboratory, where Schaefer is literally and figuratively breathing life into the modern era cloud physics, where he's forming cloud nuclei with dry ice in this cloud chamber. This led to, with the discovery of silver iodide as a kind of a more effective way to seed clouds, as it were, this led to the birth of the modern era weather modification, where they had a little bit of science or physics behind it and went off into the field and made lots of measurements, trying to seed clouds and trying to make it rain. There's a lot has been written on weather modification over the years. A report from the National Research Council, the Academy, sort of summarised the status of weather modification. This was published in 2003, but really nothing's really changed since this review. And fundamentally, the issue has been that the results of going to the field to seed clouds is fundamentally overwhelmingly inconclusive as whether we can actually modify weather or not, whether we can make clouds rain more or not. This is in part because you couldn't establish cause and effect, because there's so many aspects to the chaotic world and environment that can influence whether clouds rain or not. And simply seeding and changing one thing doesn't necessarily mean that the effect that you observe is driven by that seeding. Just can't get enough statistics from the few field experiments. So this actually was a very important, this realisation, this was realised for some time, this was realised back in the 60s, that this is a really overwhelming problem with weather modification. So this led to a really important kind of fork in the road in cloud physics. Before we even got to the climate problem, it was realised that this really gave birth to the what we now see as a modern version of cloud models, which are now becoming kind of the framework for new Earth system models. And I'll touch on that right at the end of the talk. So this really gave birth to the modern numerical models of clouds. This realisation we had to develop causality, and we can't do it in real world, so let's go to the model world and see if we can track this path between numerically seeding clouds and change in precipitation. This is where Joanne Simpson enters the fray. She was kind of a giant in our science for many aspects of our science. And this wonderful book by Jim, he's a historian, obviously. He's written more than one book, so this is another book. He's written a book about her life. And we've encouraged Jim, and we've been able to secure Jim to come to the lab to talk about Joanne Simpson and her life in the early part of June, as an attempt for the Climate Centre to celebrate diversity in our science. This will be one of the first lectures on diversity, as it were, that we're planning for the next 12 months. We're going to have a series of VIP seminars that really touch on diversity in our science. And so this will be a wonderful talk, I'm assuming, from Jim, and he'll reflect on her life, her struggles, as she made incredible progress to become one of the giants in our field. But anyway, enter Joanne Simpson. This is an amazing study that gets very little recognition. This is a study by Joanne where they built one of the very first cloud models, and it was a one-dimensional model. It had sort of dynamics of some form, but it's not the full 3D mesoscale models of today and so on, but this was a kind of kickoff, the precursor. And she was asking basic questions in this model. Could they make a maritime now? Maritime cloud is made of fewer cloud particles, so the water content may be the same as continental cloud, but the particles are larger and it tends a propensity to rain more. Continental clouds, this is cloud physics jargon in those days. Continental clouds are made of lots of small drops with less propensity to rain. So the question she was asking, could she make a maritime cloud more continental, or could she make a continental cloud more maritime? So she did these experiments numerically, and this is an experiment on the former where she took the maritime cloud, and the maritime cloud profiles, they're all in solid, and the water content profile in this cumulus cloud is on the left, and the sort of third profile in is the radar profile, which is sort of indicative of precipitation. Oh, what happened there? Oh, did I do something wrong? What is that? Can I kill that? Good job. Someone's paying attention up there. Okay. I might just use the mouse. Can you see the mouse if I wobble it around? Okay. Anyway, basically, she was able to, in this numerical experiment, make maritime clouds look more continental. Reduce the amount of rain. You can see that in radar profile, that third right here, and more cloud water. This was an important study for many reasons. It was the beginning era of the mesoscale cloud resolving models, as I mentioned. But it's essentially the very first study of the second indirect effect. done 2 decades before this was quote unquote discovered in the Albrecht study. So this was actually the second indirect effect right here, to illustrate right there in Simpson and Wigger paper of 1969. As I said, 2 decades before Bruce's famous paper. Okay, one of the most important conclusions from that study, and one that's really pertinent but not understood by the community at large today, was that the main effect of seeding supercooled tropical cumuli is through the alteration of the cloud dynamics, which in turn alters the water carried and precipitated. So what she's saying is that motions in clouds are really important, and the overall water balance of the clouds is really important. And these are the 2 issues that fundamentally shape and define the aerosol indirect effect, but fundamentally the broad community have not yet grasped this and understood it, in my view. Okay, so let's consider the shadows cast by 3 other kind of giants of our field. The first is John Mason. He really brought cloud physics to a discipline of physics, as it were, in the 50s, and his book, The Physics of Clouds, became kind of a Bible for cloud physics community. That this was still, as at that time, a subdiscipline of our science. And, you know, basically, the leaders in cloud physics for the second half of the 20th century all came via Mason's program, and we projected them into the field. The Peter Hobbs and the John Halletts and all these famous people who did all sorts of amazing stuff in cloud physics all came through the Mason school. So John Mason was really a leading figure in shaping the science and putting it on a scientific footing. The next giant in our field was Vern Suomi, and he's widely considered the father of satellite meteorology. He's really, truly the father of use of geostationary in weather in all matters weather. He was an amazing figure. His PhD was on the topic of the heat balance of cornfields in I think it was Iowa. Yeah, Iowa. And he built instruments, radiometers and stuff to measure heat flowing in and out of the cornfield. That was his PhD. On his PhD was an iconic figure known as Herbert Real, who was an iconic tropical meteorologist at the time. And he said, well, this is all great, but we must be much more interested in trying to quantify the heat balance of the planet as a whole, rather than its cornfield. Ever thought about trying to address that problem? And that led Suomi towards the study of Earth from space. And in 1959, they built together the first of the radiation budget measurements, and this was launched and failed, but soon after, in 1960, he was able to relaunch, and he was able to create maps of OLR. These are the very first maps of OLR were done in 1960, and they basically included something that's logical to us now, and we just take it for granted, that these OLR fields kind of reflected weather patterns. You know, obviously clouds and weather and stuff and affecting the OLR. So this was kind of he was really iconic in terms of shaping our move towards thinking about looking at Earth as a whole from space, from a point of view of weather. And then the third figure who really influenced our science in the sort of the middle half, the latter half of the 20th century was Sean Toomey. Now this person was, if anyone in earth sciences is described as a polymath, this is the person that would be described as a polymath. He was an expert and did pioneering work across multiple disciplines. In the background here you see the brightening of clouds by ship emissions. These are called ship tracks. These were quite basic to his some of his later research that he introduced, which became the Toomey effect. But he basically introduced this notion. Let's get some water. The notion that aerosol, once injected into clouds, could alter the radiative properties of the clouds. This became known as the Toomey effect. This was discovered first in the sugar cane fields in Australia in the 70s. And he also pioneered the study of, I'm losing my voice, pioneered the study of remote sensing of clouds from space for measurements of sunlight reflected. And he also, I'm losing my voice. He also developed key theorems in inversion theory, which now carry his name. So he's a true polymath. And now two important relationships emerged that connected cloud physics to radiation, which in turn then allowed cloud physics to be connected to broader aspects of the Earth system. The first one here was by Toomey himself, 77, and related the optical depth of clouds, that's sort of radiation, think about it as radiation processes, to the number concentration of droplets in clouds, then that's the pathway to connect to aerosol, and hence the Toomey effect. So this brought a more direct focus on the connections, aerosol interactions to clouds, and ultimately to the aerosol indirect effect. And it served as the basis for retrievals of cloud number concentrations. These have been reviewed and discussed in the last decade or so. Very approximate, gross assumptions about how you get number concentration from measurements, but nevertheless, it's sort of the basis. The second what I would consider important relationship was something that I created in the 70s. And it created a relationship between the optical depth of clouds, that's radiation, and the cloud physical properties through the liquid water path, which how much water is in the column, and some measure of cloud top particle size, effective cloud top particle size. He connected cloud physical properties like liquid water path and ice water path and so on to the radiative properties. And at that time, several kind of cloud feedback ideas started to emerge all around liquid and ice water content change. So as the planet warms, clouds get warmer, they hold more water, the liquid path increases, and that was a kind of perceived to be a negative feedback because the wetter the clouds are, the brighter they are, the more sunlight they reflect and so on. So there are a lot of ideas about feedbacks based on water content in clouds in those times. It kind of introduced or elevated the effective radius as like a cloud property. There's a lot of debate in the time about what does this radius actually mean? Is it actually really a cloud physics property, or is it just some sort of conversion of liquid or ice to optical depth? Does it have any tangible physical meaning, basically? And so this relationship also became the basis for remote sensing liquid water path from optical measurements like from motors. And I was contacted back in the mid-70s by the microwave community who were just starting to develop microwave measurement techniques with microwave radiometry, imaging radiometers, and Stalin, for example, 1976. And they contacted me about, well, gee, we think we have a way of measuring liquid water path using the microwave observations. And so, we have a way of measuring that. So you'll be able to explore this relationship with our clouds and radiation and all that kind of stuff. So it sort of gave a rationale to connect to these developing new ideas about how to use microwave observations. Okay, now let me move into the era where cloud physics has moved away from being just a sort of an interesting subdiscipline, sort of heavily tied in the early stages to weather modification, ultimately to a global science that it is today. And this occurs through cloud physics and climate change, the effect of clouds on climate, and it affects in very profound ways through feedbacks and through through the radiative forcing, through the indirect effects of aerosol affecting clouds and so on. And these are two giant impacts on our ability to predict the warming of the planet as greenhouse gases increase. These substantially, to zeroth order, affect our ability to calculate the global warming. So let's just kind of touch on this a little bit. So this is the sort of the notional structure of the community in terms of describing or thinking about climate change and global warming. And the kind of the language or the currency is what we call the equilibrium climate sensitivity. This is effectively how much the planet will warm if you did instantaneously doubled CO2 and let the system with all its feedback take place and evolve back to equilibrium. How much would this planet warm? And this is sort of long and slow. It occurs on, like 70 years or even longer time scales. So you think about this sort of mentality is really feedbacks that are really slow and sort of affecting the slow component of the whole system. So and how it works is it follows It follows like the Gregory method, which postulates that the top of the atmospheric flux at top of the atmosphere has which is obviously the absorbed solar minus the emitted long wave, that postulates that a change in this net flux can be thought of in terms of some factor that's characterised by the forcing, this instantaneous forcing double CO2, you get some impact on top of the atmosphere. And then you've got some response that's related to the temperature of the system that then describes the feedbacks, right? So this is sort of the Gregory sort of analysis. And so it kind of works this way. It turns out this is not a good example because this is actually the example to the left. I wonder if I can use this. Yeah, the example to the left is actually a 4 times CO2. So you have to divide all these numbers by 2 if you want to get back to the traditional equilibrium climate sensitivity of 2 times CO2. But basically, the way this works is like this. That you basically, this intercept here in the y-axis is a measure of the forcing. That is how the imbalance of the top of the atmosphere has occurred when the global mean surface temperature change is 0. And then it evolves over time back to an equilibrium by forcing it in this way. And this magnitude is the forcing. And the slope represents these feedbacks. And the intercept at the 0 line represents equilibrium climate sensitivity. And so the equilibrium climate sensitivity is shown here for CMIP5 models and the CMIP6 models. And so these are basically the values of kind of intercepts from this sort of analysis. And basically, one of the things, and there's been a lot of discussion about this in the literature, about the way the models now have pushed their climate sensitivity to even warmer temperatures, right? And there's a lot of discussion about this, some explanations for why this is the case. And essentially, to make a long story short, both the spread in these models and the difference between CMIP5 and CMIP6 is effectively associated with the different ways feedbacks are represented in models, but mostly the cloud feedbacks in the models. So most of that spread is argued to be mostly cloud related. And the difference between 5 and 6 has been argued to be specifically cloud related, specifically associated with mixed phase clouds and over in particular southern oceans. So it's just to sort of highlight the importance of these feedbacks on the system in this context, in terms of slowly evolving climate change and where the planet is moving to in terms of its warming in the context of something like this equilibrium climate sensitivity. So these feedbacks are sort of slow, if you want to think of it that way. Well, the kind of the language and the kind of, I guess the currency in terms of analysing feedback is typically kind of done in this way. You think about a planet that's overcast and a planet that's clear sky, and the difference between these direct effects of rate of clouds on the radiation budget, long wave and the short wave budget. You've got long wave as influences what's called the greenhouse effect. So clouds are colder than the equivalent clear skies. So this tends to be it's defined in such a way this is positive greenhouse effect, and the short wave effect is cloud. The planet is brighter than the clear sky normally, and so the albedo effect produces is a negative contribution to the net energy flowing into the planet. So what typically the community does is it typically looks at the this change in these radiation-based quantities for a given change in sea surface temperature, global mean sea surface temperature. And this is taken to be a measure of the feedback. But this is really makes some assumption about causality, that the given change in net warming of the planet is responsible directly for the changes in the clouds that you see. All right? So that's how we measure, that's how the community is quantifying or measuring the feedback. And so you get diagrams like this, which come from Salinka, where these measures of this change in the radiative properties of radiative effect of clouds for given warming of the planet is shown here in the y-axis, and you've broken down by all different cloud types. And the low cloud over here has a big range in the net radiation. So there's the net radiation that has the biggest uncertainty or range or intermodal spread, and that's sort of is interpreted to be that the low clouds are really driving an uncertainty in cloud feedback in the context of these slow processes. But this is really not the full story. In fact, it's far from the full story, and I think the community just tends to be fixated on these kinds of little metrics and not ask a set of questions. So, for example, Look at the high clouds. The high clouds have a big range shortwave and a compensating range long wave, leaving a rather small net change that the community says, oh, this doesn't really matter because it's a small change in net. This is not really the full story, as I said, because this change in the long wave is occurring within the atmosphere. It's associated with clouds and the way they heat the atmosphere. This change in the short wave is actually occurring at the surface, and particularly in the oceans. And so these manifest themselves on very different timescales. So you've got feedbacks now occurring through these changes that are occurring not on the 70-year time frame of this slope that you see from the gravity plot, but these are occurring on different timescales and are very pertinent to weather, climate, and regional and climate change on different timescales. And one important example of this, which we've written about, is the ENSO system. The ENSO system is a feedback system involving the differences in the way the heat gets deposited from the atmosphere into the ocean and the feedback that couple these, that take place in this coupled system, occurring on scales of months to a few years, not on 70 years. So this fixation on measuring feedback this way and saying, well, this is the most important because this is the biggest range here, as I said, is far from the complete story. Okay, so this point alone was one of the driving forces behind our thinking about CloudSat. We wanted to ask questions about how much does the heating through the column change when you're in presence of clouds. This was one of our driving questions of CloudSat. We were able to, in order to do that, of course, you've got to be able to measure the vertical distribution of cloudiness, and this is really the first real depiction from the A-train of the zonal distribution of cloudiness. And I'm not going to spend time on this diagram, but basically we're able to answer the question, how much heating does takes place and what does the clouds do? So if you look at we'll just take this figure here, this one here. You look at the globe as a whole, it looks like the short wave, if you have these global metrics like equilibrium climate sensitivity, it looks like the short wave changes is what drives the net change, as we saw in this Linker kind of analysis. But if you look regionally, the tropics is driven by the long wave change, effect of clouds in the long wave, changing the long wave, and that's driving the basic net that you see in the tropics, and conversely, the same story at the poles. So you've got these big gradients of heating within the atmosphere that you don't see, and the long wave is a driving mechanism, but you don't see that also when you smoosh things together globally. So these global metrics of feedbacks, I would argue, are just really give you a really incomplete story about how the system couples and evolves, and the important feedbacks that really operate within it. Okay, now let's just reflect a little bit on the early era of cloud physics and space. I'm just going to highlight a couple of examples, and these are fairly common with our field. The cloud physics from the microwave emission, going all the way back to Stalin's correspondence meeting in 1976. The difference, this is basically measure, it's a little cartoon how it kind of works. Basically, the ocean in the microwave is cold because of effectively the emissivity of the ocean is like 0.4 or something like that. Basically, there's significant reflection of microwave energy off the atmosphere into back to space. And now, so when you have a kind of a highly absorbing emitting media like clouds or water vapor that effect across the ocean, the emission is increased because this is coming from a much warmer temperature than the effective emission temperature, the effective radiating temperature of the ocean. And that degree of warming is directly proportional to whatever the absorbing emitting stuff is in the atmosphere. And that leads us to ways of dissecting and getting the cloudical water path from the microwave. And indeed, that's sort of the basis for getting precipitation from microwave as well. The other method that's really common and being widely used is the sort of bispectral reflectance method that Toomey introduced in a study by Toomey and Seaton back in about 1980, I think it was, maybe late 70s, early 80s. And this is popularised by Nakajima and King, but it was really Toomey who kind of pioneered this approach. And basically, it's a sort of simple idea. You have measurements at two wavelengths from the reflected wavelengths from the sun. One's at a visible wavelength, where the amount of energy reflected is primarily a function just of the optical depth of the cloud. And one's in a near-infrared wavelength where absorption is taking place, and where the reflection is a function of the product of the optical depth and an optical property that really carries signatures of the particle size. And so by making these two measurements, you could cleave apart the optical depth bit, the visible, and the particle size bit, and get separate measurements of the particle size and optical depth via this relationship that I mentioned before. And so you can get the liquid water part. So, oops, I hope you can move it. Do you can move it? Oh, okay. And so these are some examples of data collected, both from the microwave and from MODIS. And this is only 14 years of the MODIS, but there's a lot more than that now, of course. So there's a liquid water path distribution. It's ocean for the microwave, because obviously the oceans are a kind of a stable, cold emitting surface. If you do it over land, then the land surface is the temperature near the cloud temperature. The contrast is less, and the emission from the land surface is much more variable depending on soil moisture and all sorts of complexities. So it tends to be, these products tend to be, from the microwave, tend to be primarily ocean-based. The liquid water, optical depth, and effective radius from the MODIS product is sort of shown there. So I'm not going to speak to the patterns of these, but some of you know these well. But just sort of give you an idea that we have, 30 plus years now. When this was written 2 or 3 years ago, it was 29-year climatology. We have more than 30 years climatology now of the water and how it's changing, at least for warm clouds. We have multiple decades now, I would suspect, of the effective radius and stuff of clouds. Okay, from MODIS. Now, okay, so if you have got all this data, what do the present day climate models look like with respect to the water properties of these clouds? And this is sort of highlighted here in this Taylor diagram. This blue dot is the observation from the microwave, and the various models participated. I think this is CMIP3. This was actually an early study, CMIP3, but the difference between CMIP3 to CMIP5, CMIP6 aren't that different, so the models haven't really addressed these biases. But basically, to make a long story short, there's a major bias in the models representing just the water content of low clouds. When we're talking about biases, the order of 100% more. What we find is that the clouds tend to be way too wet, way too much water in them compared to what we observe. And in order to give you the right kind of energy balance at the top of the atmosphere, because the models are tuned to that, you have to have too few of them. You have to have a reduced number of the clouds because they're way too bright, but they're way too few. So it's called the too few, too bright bias. And this is, I think, a fairly serious bias, given that, the arguments about cloud feedback and low clouds is centered around low clouds. And this is a fairly large bias with respect to low clouds. Anyway, okay. Another question that was posed, and it was posed from the outset, was this effective radius. What the hell is it, and what's it mean? This is an example of the distribution effective radius for MODIS, and the difference between land and ocean effective radius. Quite a lot of difference between land and ocean. And the questions were asked continually: is this just a retrieval artifact? It probably doesn't mean anything from a cloud physics point of view. Has no real cloud physics basis behind it. So this was a debate that went on for decades, actually. And here's an example. Here's an example of the GFDL model. A version of the GFDL model was published by Leo Don in 2011. This is their version of the effective radius for warm clouds, and this is the MODIS observations. And they're just like the kind of almost two different planets. The argument was, well, these aren't physical anyway, so this doesn't really kind of concern us. Well, I'm going to argue, and then my mind changed, because I thought it was kind of effective radius was more or less just like a radiative property, like a conversion. But no, what we find, and what we found with the cloudset observations, that more than 40% of these maritime clouds, we see these large particles, have drizzle. And that these large particles that we see with MODIS are actually reflecting something about the cloud physics. I'm going to kind of illustrate this in a minute. So gets me to the cloud physics from place, our golden era. I'll call it the golden era. It's the golden era of the A train. As you probably all know, I've been a champion of the A train for many years. So with this A train, we could begin to answer many of the questions raised by the early observations, and we could do this we could set this on a global footing, and we could also go further. Than just thinking about cloud properties. We could start to begin to explore processes. I'm going to kind of highlight this in a minute, what I mean by this. This was kind of in my mind, golden era. But as we build up to the A train. This A train, I've always believed that sort of the fulcrum of this A train were the active instruments that really told us what's in the column and where it is, so that we could start to better use the passive information to hone in on what it is we're looking at and quantify these properties. So I've always argued that these active instruments was kind of like the fulcrum in this chain of observations. And in getting to this point, I just want to take a little light aside, because not many people know about this. I thought I'd just sort of share this story with you. The Light Shuttle was launched in 1994 on the Discovery, and it produced 11 days of LiDAR orbit data. And this was like the precursor to Calypso, but it was kind of whet our appetite, and whet appetite more generally for the active instruments and the insight it offers us. And so it played quite a role as we started to plan for CloudSat, actually. And we did this study. We went to ECMWF and said, listen, we got these 11 days of LiDAR data. Can you give us your best analysis for those 11 days so that we can start to do comparisons one-to-one? And they raised their finger and said, okay, we will do that, but you can't publish anything until you sit down with us and we'll just discuss it, because they were a bit concerned that their analysis wouldn't look that good when you start to probe questions about where the clouds are and stuff. And we didn't have any idea. So, sure, Tony Hollingsworth, sure, Tony, no problem. We'll share anything you want, and we won't publish anything. We just want to do this to sort of get our mindset as we start to write the CloudSat proposal, which is middle 90s. This was a study by Miller, published in 1999. And the upper curve is the ECMWF, upper panel is the ECMWF cloudiness on the ECMWF analysis grid, the height, and there's a sort of a spatial context. I don't know whether it's 1 degree or whatever it was, but the cloudiness information it's volumetric cloudiness in this case. So every volume of height and horizontal sort of grid spacing was a cell. So every time a cloud appeared in that cell, you'd count it and you would compare it with the light observations. The light observations matched to the ECMWF sort of scale is on the bottom panel. This is just one part of an orbit, right? And so Miller did this full statistical analysis, and the results were just completely mind-blowing. This is back in the late 90s. So the overall cloud fraction for the entire cell for these 11 days, remember this is volumetric, not area. The cloud fraction for the volume, light said it was 28.4%, ECMW came up with 28.9%. I mean, this is like, what? The hit rate, that is how frequently did clouds appear when the observation said they appeared. How often were they there when the observation said they're there? 87%. I mean, this is mind-blowing. And this, basically, when we shared this with ECMWF, they were not only so excited, this actually, people don't realise this, but this actually set the path towards cloudy sky assimilation of radiances. They started that with these results, say, well, hell, we think we can get clouds basically right most of the time. Therefore, we can start thinking about assimilating information in the cloudy sky to improve our forecast. And it took 15-some years before they started to do the microwave cloudy sky radiance assimilation. But this was the starting point to moving down that path because of the results were amazing. It also meant to us that we would have analysis of the atmosphere that would map to the clouds that were seen at that time, because clearly the clouds were pretty close to what we saw. So we had full faith that we knew what the environment was in which these clouds were forming. And so it sort of added strength to our argument for CloudSat and the A-Train. Well, the A-Train arrived with a bang, as we know. This is, I don't know whether you recognise it, but that's the A-Train poster at Caltech. And this was shown in an episode of Big Bang Theory. You can see the poster. I don't know who created that poster. I don't know whether it was JPL or whether it was Goddard or NASA as a whole. But anyway, that's the classic A-Train poster. And we appeared in Big Bang Theory, so we knew we'd arrive, folks. So with the W-band radar, I'm going to do a little bit kind of self-centric here with the radar observation. We combined this with other A-Train assets. We really just started to develop important cloud physics capabilities. We could study clouds and rain jointly for the first time. We've not been able to really do this in a joint way before. So we could actually say important things like how rain was formed, for example, we could make definitive statements about how often it rained and snowed in the planet for the first time. We had never had this really before. We had wild guesses from all sorts of precipitation observations that had no real measure of the frequency of rain, and still don't. We are able to identify that models basically made rain too often. So this is a diagram. This diagram shows a number of different models: UK operational models, climate models, and high resolution like cloud models at that time. And the currents of precipitation. We have a couple of different cloud set observations, depending on how you do the scaling to match the observations to the model. But basically, bottom line is, no matter what we did, the models were always producing significantly more precipitation than was observed. They had this perpetual, what I call dreariness in the models. As we go now to the present day kilometre scale models, we're going to say a little bit more about this as I just approach the end soon. CloudSat, this is the CloudSat observations on the scale of the UK Met Office 5 kilometre model. This is from what's called a diamond comparison, which I'll touch on later. Basically, and this is sort of the same format as this diagram, shows you the observations of CloudSat and two different kilometre scale models. The dreariness of the models perpetuates even with the move towards this kilometre scale Earth system modelling that we are steadfastly approaching. So it hasn't gone away. And this matters one hell of a lot. And this is one of the reasons why it matters one hell of a lot. This is an example of the global warming, historical record of global warming. It's by a study by Gold et al. In 2013. It's the historical record compared to the observed record. The observed records are black and grey curves here. And the historical record from the model is represented by three different model simulations. The difference only in these simulations is the knob that they turn on, they have that turns on when rain forms. And just to cut to the chase, the more realistic rain formation example, more realistic when compared to observations, is actually this blue curve. Yet it's the furthest from the historical record. The 6 micron critical radius that turns the rain on makes the model way too dreary. Yet it gives you the kind of observed kind of temperature record. So this matters one hell of a lot. You know, whether you get it's raining right, the right sort of frequencies, it matters enormously to not only the feedbacks but also the way the aerosol indirect process occurs. I'm just going to quickly go through this. I'm running out of time. I just want to highlight an illustration of process and how we sort of think about process and how we can use observations to say something meaningful about process. In this case, it's going to focus on rain formation process since it's kind of an important topic. So you have a simple model of way rain forms is through the coalescence of a big drop collecting smaller drops as it falls through. And you go through and build a simple model, and you can predict from that simple model a relationship between an observable, the radar reflectivity, and the optical depth of the cloud, which characterizes the smaller drops. So the reflectivity is sort of a characteristic of the large drops, and the optical depth characteristic of small drops. And you can show in a simple model, cloud physics model, that this gradient of this relationship between these is directly related to, in this simple model, in terms of how effectively drops can be coalesced, be collected and form the raindrops. And so, simply put, you can, by looking at the relationship between the reflectivity observed from CloudSat, for example, and the optical depth observed from MODIS, you can look at data composited this way, and this is for an effective radius cloud top of 5 to 10 microns, and that there's no real slope in this relationship, so there's no real coalescence taking place, so rain's not forming in this cloud, right, according to this, if you look at through the lens of this cloud physics model. As the particle sizes get observed larger in MODIS, you start to see sort of elements of this coalescence process taking place. As it gets larger again, you start to see real evidence of the coalescence and precipitation occurring. So this is what I mean by looking at getting a handle on processes. And this was published in a serious paper by Suzuki et al. And this is very important because this is why I say the effective radius is reflecting cloud physics. It actually reflects the precipitation process. The bigger the drops we observe from MODIS, the more likely it is that the clouds are drizzling or raining. That's pretty kind of simple notion, but that's kind of what we observe. When you look at what models are doing, this is the observations from the A-train grouped by kind of the cloud top effective radius in 3 different group bins. And these are 1, 2, 3 different climate models, and they all are making rain all of the time. Where in the observations, these two ranges of particle size, there's no real rain forming in this case, a hint of like light drizzle in this case, and then rain starting to form as the drops get bigger. So the models are making rain all the time. So 2 key points. The effective radius indeed reflects cloud physics, I would argue. There's no model drizzle rain sensitivity to droplet size. So I'm going to short circuit and just sort of describe some, coming back to full circle back to the indirect effect and seeding, and the indirect effect and weather modification. So the indirect effect, simply for those who really aren't all that aware of what it means, is basically we have a cloud that forms in an environment where there's increased aerosol. It might form as a result of like the ship tracks, it might form in a more highly polluted air mass. The clouds that form in that condition will form, the argument is that they've got increased CCN, smaller droplets, and they therefore for the same amount of water in the clouds, they reflect more. This is regarded as the Toomey effect or the aerosol indirect effect. But there's all sorts of complications take place. You make the drops smaller, they drizzle less. And so the water content in clouds increases and they reflect more. So it's a very complicated effect that has very large uncertainties. So let's just now go to the concurrent comparison between indirect effect and cloud seeding, because there's really important parallels here. The hypothesis is that the cloud seeding, the modification of microphysics produces a macroscopic effect. That is, you change microphysics, you get more rain. The indirect effect is you change the microphysics, you get brighter clouds. That's the hypothesis. So it's very parallel, right? In terms of cloud seeding, the response is not simply predictable from given microphysics forcing. Just changing microphysics doesn't necessarily give you that response that you expected. Similarly, just changing the microphysics doesn't give you the macroscopic forcing or brightening of clouds that you expect. And I can discuss this more offline. The main effect of seeding is through the alteration of cloud dynamics, which in turn water carried and precipitate. That was the conclusion of Simpson. This is also true of the indirect effect. Now, one of the basic differences, which I won't have time to go into, is that with cloud seeding, the in-field measurements, there's so few of them to eke out statistical cause and effect. You just couldn't do it with it. However, with respect to the indirect effect, we have now global observations. We have anthropogenic phenomena such as ship tracks, natural phenomena like volcanic eruption. We can start to eke out causality from a very large body of data. And that's something that we can now do. I'm going to skip over these because I don't have time to talk about this. And we can now do. So let me just now summarise in this as reflect on going forward. So what we've been able to do, what we've seen in the last 50 years, is advances from the early days of cloud physics, which were primarily locked in the laboratory, or then moved with aircraft measurements that were very kind of local in terms of its characterisation experiments. We're now at a point now, and we see this like with the last 20 years or so with A-Train, is we've now closed the gap between the kind of the microphysical and cloud scale kind of processes that were the focus in the first part of the evolution of cloud physics into now a truly global scale. We can start to see these processes now mapped globally. These multi-sensor approaches that we've developed over the last 20 plus years have exposed a number of shortcomings in models, such as the dreariness of the models, revealed genuine insights and processes essential to quantifying cloud feedbacks and forcings, and we've pointed to really important ways to address persistent biases in models. I won't have time to talk about how these observations are really starting to influence the development of models and improving models. Let me just now close with these next couple of view graphs. And this is the image of the blue marble. This was taken by the Apollo 17 astronauts as they steadfastly flew to the moon in 1972. This image is considered to be one of the most sort of consequential images ever taken, because It's influenced the human consciousness, the global consciousness, the environmental consciousness. And according to Wikipedia, obviously it's an important source, according to Wikipedia, it's the most reproduced image in history, right? It probably is. Now I'm going to show you another image that just truly represents another dimension to the human spirit. This is the spirit of boldly go where no man has gone or no person has gone. This is an amazing, I'm about to show you an amazing image. And you nerds in the audience will sort of look at this and say, well, this is different. You know? I'm going to show you a 2-day forecast done by the Max Planck Institute in conjunction with the German Weather Service at a kilometre scale coupled ocean atmosphere kilometre scale model that they've now developed and are doing experiments with. And they did a 2-day forecast for this time, for this day. And this is their forecast. And this is truly amazing because I'm just stunned by these two images. You know, some will say, well, you got more shallow convection in the model versus the old world because different camera, different resolution, you know. But this is just elevates the kind of human spirit. This one of the things that we really strive for is to try to understand Earth and how it's changing. This is amazing. To juxtapose those two images together, to me, represents amazing progress. So as we look at the outlook, we have really evolving this digital twin Earth. Destination Earth is a major new initiative in Europe, all around K-scale modelling of Earth, right? We have the Diamond, which is a multi-model K-scale in a comparison that Bjorn Stevens has written an article, introduced in 2019. Julius Slingo wrote an article that's calling for really when we need an ambitious sort of partnership worldwide to really advance the use of these kilometre scale modellings to really start to develop Earth system models on this scale. Sue and I wrote an article on the question of how bad will future rains be. So this is a question that just haunts me still, and introduced the notion of decade convection. So these represent things going forward and why we think progress is going to occur. So let me just go to this question about how bad will future rains be. I said it's a haunting question. UK Minister asked this question of chief scientists in England in 2016 after massive summertime flooding from thunderstorms. He just asked a simple question: how bad do we expect these rains will be in the future? And we can't really answer that, right? We can say, well, we expect storms to get more intense and hand wave, like 7% closure clapper and stuff. That's just like hand waving. So we can't really answer this question. So, but I would submit that we need, as a minimum, a different class of models like these kilometre scale models or even finer scale. And these two panels on the right show you the PDF of rain from different resolutions of model: 14 kilometre, I can't even read that myself. 7 kilometre, 3.5 kilometre, 1.7 and 870 metres. So this is one panel. This represents the Diamond simulations compared to GCM climate model simulations. The climate model PDF of rain is a dotted. The black solid is GPM. I guess it's iMerge. Take that. You have to take that as a grant, so it'll be an observation. We'll consider that. And the solid lines are the Diamond model results. The bottom line here is that in order to capture the more intense rains, we would think that you have to have a higher resolution than we have. We can't address this with the current day climate models. You just can't address questions like how bad will rains be, even though communities out there probably trying to answer with climate models. It's clear that you need to resolve processes that really make the intense rains, like convection. Okay, so this leads me to the last couple of view graphs. The outlook towards the future is one outlook. This illustrates one of the outlooks going forward in the observational area is INCUS mission, which is designed to go after the transports associated with deep convection, and it tries to do that through a novel use of small satellites with radars, the RainCube radar expanded to fit on these and measuring the reflectivity seconds apart, and the reflectivity change in time is a measure of the transport associated with these convective storms. That's quite pertinent to understanding and answering that question: how bad will future rains be? The second is and that second in the outlook is thriving on our changing planet. The decadal survey called out specifically clouds of convection and precipitation as one of the DOs, and that in turn is focusing on trying to introduce the next generation of observations that involves motions, the motions within storms and clouds. So that's that represents sort of a pathway, at least from the point of view of the Earth observations going forward, to try to make some progress with respect to ultimately answering this question. So I'm going to, this is my last slide, concluding comments. I would argue that the decade of 2020s will be a decade of convection. And why convection? Well, this could be in another whole seminar of why convection, why it's such a seminal part of the Earth system. I'm not going to go into that, but it's quite fundamental. But to imagine if you have, in your weaponry, a bunch of arrows that represent all sorts of capabilities that are emerging this decade. I've just talked about AOS and Incus. We have the Sentinels and the geo-ring radiances from the geostationary now is really developing and positioning ourselves in the program of record to be able to do things we haven't been able to do before from geostationary. We have sustained measurements of precipitation continuing through the decade. We have this kilometre scale Earth system models right at our doorstep. Destiny, Digital Earth and Diamond, for example, are elements of this. We have kilometre scale hydrological modelling also occurring from the community of the hydrologists. So all of these are tools that we see that you can imagine are moving towards a clear target, and that target would be asking questions about how bad will future heavy rains be, the changing nature of our fresh water. So we expect that we could make some semblance of progress on this really important taxing question, and that we have a number of opportunities in the coming decade. And it's because of these opportunities focused in this way that I would argue that this represents a real decade of focus of convection. So I would call the 2020s as the decade of convection. That's it. Thanks. Oh, it's a whole hour. Dragged on a bit long. Okay. Questions? Well, you have questions online?
Oh, no, not.
Any questions? Feel free to use the mic. Oh, the question.
You don't have to.
So Graham, I have a bunch of questions, of course, about the climate scale global cloud resolving models.
Yeah.
But there's a couple of them that I think may be worthwhile debating a little bit, which is people that are trying to understand convection from a modeling perspective, they use the LES of convection. So they actually use, so that, I think there's an arrow that is probably missing there, which is people that are using, fairly high resolutions of 100 meters or less to understand convection. In small domains, of course, not global domains. So how do you think the strategy should be about bringing together the fact that there's so much energy in this climate scale global models, but the people that really trying to understand convection from a modeling perspective don't really look at those resolutions. They actually look at LES resolutions, and they would argue that 1 kilometer is not enough to resolve convection, right? So how do you bring those two things together?
Yeah, so I guess it's a matter of where all the action is in respect to, is it in the mesoscale or is it in the finer scale? So look, if you look at this figure, where is convergence? I mean, 870 meters doesn't mean it's converged either. So we actually don't know what scales you have to go down to answer questions about the most intense rains. It may be LES scales, but probably not. It probably is a scale that requires you to resolve at least mesoscale circulations of large weather systems and storms. It'd be my guess, but we don't know. But what we do, I think, know is you're not going to be able to say much about intense rains without going down and beginning to resolve something at smaller and smaller scales. We just don't know where that needs to be, Joel, and that's part of the research, I would think.
Do you know if ECMWF is planning to move away soon from their 9-kilometer resolution?
I know that they've done forecasts and run the IFS at 1.5 kilometres. That I do know. I don't know whether their plan is to move to that scale for IFS as a whole. And you know, just move, and I think it's necessary. You have to go change the scale of these models to answer these basic questions. I don't know what the scale ought to be, but I think it's necessary. But it may still not be sufficient. You know, just because we go down scale doesn't mean we're getting there either. But I think what we can say is you can't say much about extreme rains with the current suite of climate GCMs. You just can't say it. You're just not resolving things that matter. And even at the kilometre scale, you might argue we're not quite resolving it, but at least you can resolving things that you can associate with air going up, being lifted up, even at a core scale. And you need at least that to make intense rains. So anyway, I think this is really where the debate will go in the coming decade.
Other questions? Go ahead.
Quick question. So the A train's kind of in the later stages of its life, and do you know kind of what's sort of the next version of something like that that's going to do all the radiometry and the active measurements to kind of keep things going?
I think the hope was that the AOS observing system, I didn't have time to go through it in detail, but the AOS is a combination of active and passive observations. The hope was that would start to build some elements of the A train, rebuild it. But you know, with the costs and the cost caps and the growing costs of all sorts of stuff going on, we just don't know how much we can even build like foundational parts of the A train back with the AOS. But that was the hope. And then like the A train, once you build a sort of a framework, other things happen, other things come. And we learnt that. And so that's the hope. But again, I'm not sure. We just don't know how much of the vision of the A train will be able to be carried through with the AOS. But that was the plan. Evan. Oh, hang on, I need to read it, don't I? Okay. Evan has a question. Evan, do you have any thoughts on how spatial resolution of space-based sensors affects the ability to test climate models? Only a kind of a general comment, Evan. One of the important things I think gets overlooked is that with these kilometre scale models, limited as they might be, Joel, the kilometre scale models, the resolution of those models is much closer to the resolution of the intrinsic observations we're making from space. So therefore you're at a position where we can kind of compare apples to apples. So if you take convection, for example, and you use it in GCM in a climate model, the convection in a grid box is sort of made up, it's statistically sort of made up, basically. So how are you going to take an observation that's a kilometre and compare it to this made-up statistics? It's very difficult to do. So having them more on this common scale will make a direct evaluation and comparison, I think, cleaner and more insightful. Question then is, what kind of resolution do you really need in the observations versus what resolution in the model? I think that's still open a little bit, but I would argue from the point of view of freshwater resources of the planet and how rain's forming and falling, I suspect that gets organised on a larger scale than just on the small turbulent scale. And then capturing that organisation on that scale is probably important. So it's not a clean answer, but I really do believe that having the ability to have models that reproduce, that can simulate observations on the same scale, is going to lead to more advanced use of the observations and ultimately to improving the models. That'd be my thought. Yeah? Another one? Ian, yes. Ian, what are your thoughts about the advances in ground-based and aircraft aerosol measurements in understanding AO clouds? Is that another arrow in your last chart? Well, the last chart was more about convection and convective processes, but I think that you probably, it's hard to conceive of getting the exquisite microphysical measurements from space that you can get from the surface or from the airborne. So that'll always be part of the mix, Ian, as you well know. And the AOS program has a kind of has an element of what they call suborbital, which is about making measurements that you can't try to really fully extract from space. So I think from a point of view of your strategy to advance the questions, the suborbital becomes an important part of the whole mix, which it is in AOS. From the point of view of convection, suborbital will also play some role, but we've had a lot of suborbital observations of convection over the many years, and we still struggle with representing convection in models. So it helps, but it's not going to give you the answers that we need. We need to be able to do this on a large scale, trying to understand how convection interacts with the environment. So that'd be my shortish. I know I'm sort of avoiding the real details of the questions, but that's sort of a general answer. That's it? More? No? All right. Thank you, guys.